In a country as sunny as Australia, you'd reckon every rooftop should have a solar panel on it. But the uptake of solar has been quite slow, mainly because of cost. Well, a consortium of Australian scientists may have an answer that's right on the money. Mark Horstman investigates.
Every hour, there's more energy from the sun hitting the Earth than all of the energy consumed on our planet in a year. But our use of solar technology to capture and store that energy is still just a drop in the ocean. One problem is the silicon solar cells we're used to are expensive and difficult to make. Now, many labs around the world are making polymer solar cells out of plastics that don't need silicon.
The advantage of polymer is that it can be twisted, it can be moulded, it can be shaped, so it could go on rooftops, providing it can survive the sunlight.
But the biggest advantage is polymers are cheap. And when it comes to producing them in bulk, Australia has a head start. Jerry Wilson and his funny money have a lot to do with it.
This was a $7 note that CSIRO printed back in the 1970s.
$7?
$7.
Took off?
Not really.
But it's what it's made out of, which
Yes.
is the important thing.
And this was our first foray into making polymer notes.
Along with the boomerang, the secret ballot and the bionic ear, there's another Australian invention that swept the world, the plastic polymer banknote, made here on this giant printing press. Australia's already exported around 4 billion polymer notes to more than 26 countries. To understand what printing plastic money has to do with solar cells, we need to make one in the lab.
The aim of the research is to effectively make solar cells so cheaply that it's a logical choice then to use solar energy rather than any other sort of energy.
Polymer solar cells are made of a sandwich of layers that transport electrical charge. One donates electrons, another accepts them. Light energy excites the molecules of the polymer enough to make the electrons easier to pull away.
And that's where the key is, to get light absorption to promote an electron from a tightly bound state to a weakly bound state, and then to extract those electrons as quickly as you possibly can.
A gradient of energy across the layers pulls the electrons towards an electrode.
We've got our aluminium down here, which we're going to heat and vaporise.
So as the metal vaporises, it rises up and sticks onto the solar cell you're making.
It then covers the back of the solar cell, which gives us the second electrode.
What kind of light can these solar cells work in?
They can actually work in low light, so they can work inside as well.
So artificial light as well as sunlight?
Yes.
Here's the test. And look at that. Works like a charm. That's some milliamps. Is that a good response?
Yeah, that's a good response. These are very, very small solar cells. We would expect in this simple cell to have 3 to 3.5% efficiency, which is pretty much standard around the world for these materials.
In experiments with new materials, they hope to get above 10%. By comparison, silicon solar cells can achieve 25% efficiency. But it doesn't matter that the polymer cells are less efficient if they're much cheaper and quicker to make.
Then away it goes.
With another kind of printable solar cell, researchers at Monash University have achieved efficiencies of 11.5%.
What we're printing here is titanium dioxide. So this is our replacement for the silicon that you see in commercial solar cells. Titanium dioxide is a semiconductor, just like silicon.
The revolution is just a t-shirt away.
So you just squeegee it onto the glass plate?
We just print it like you would print it a t-shirt. So our trick with this technology is to die that will sit on top of the surface of this semiconductor and capture the light and convert it into electricity.
Once researchers figure out how to make them durable, they're ready to go from benchtop to rooftop.
If the world had about 6 100-kilometre by 100-kilometre grids of 10% efficient solar cells scattered around the world, we would be able to satisfy the world's current energy needs. These plastic solar cells, we're not restricted necessarily to put them on land. We could use them to cover our dams, to stop evaporation. We could use them in the ocean.
The ability to use existing factories to print these solar cells makes them ideal for mass production.
If this high-speed printer were printing solar cells, it can do around 200 metres every minute. That's about 100 kilometres every day. And at that rate, in just 2 months, it could print the generating capacity of a coal-fired power station.
And that's got to be a licence to print money. Here at Securency, they're rolling out their first proofs of polymer solar cells 6 months ahead of schedule and just in time for a clean energy future.
You can teach someone chemistry, but you can't teach them passion. And there are a lot of people out there who believe that they have an opportunity to contribute to a global solution to an important problem.